In this session, we're going to look at more applications of exponential functions. First one is going to be radioactive decay. How long does it take for 2.4 grams of carbon-14 to be reduced to 1.3 grams of carbon-14 by radioactive decay if the half-life of carbon-14 is 5,730 years? First, let's remember the model that we're going to use. Different books use different notation, but this boils down to we're using A is equal to PE to the RT. In the context of this model, what information have we been given and what are we looking for? First off, we're told to find how long it takes. I read that as find t, which is really confusing because the first thing we're going to do is not find t, and I'll show you why in a minute. If we start out with 2.4 grams of carbon-14, now that's the P, and it gets reduced to 1.3 grams after time. Well, that's the amount that you have after time, and so that's the A. What's up with them telling us that this half-life of carbon-14 is 5,730 years? What is half-life? Half-life is the time it takes for a starting amount to be reduced to half of what it was. And so it's the time for an initial amount P to become half of P. Here's the thing, you might be tempted to flesh out the equation right away, substituting 1.3 in place of A and 2.4 in place of P. And so you might be tempted to say that 1.3 is equal to 2.4 e to the RT, and then for t it's 5,730. This is totally wrong. And I will tell you why. Two reasons. One, if I knew that the time was 5,730 years, it'd be kind of silly for them to be telling me to find out how long it takes. That's number one. Number two, it doesn't take that long, 5,730 years, for 2.4 to become 1.3 grams. It takes that 5,730 years for the amount to be cut in half. Okay, so the way we're going to use that information is we're actually going to set up an entirely different setup first. That is, we're going to say if my initial amount is P, and over time I end up with half of that amount because of the half-life, and I know that that time is 5,730 years, then what I can actually do is I can use that to find the rate of decay. Once I have the rate of decay, then I can plug that number into the equation for R. We know what P will be, we know what A will be. Now we only have the one variable T, you see? So, our steps at this point are going to be to isolate the E and then solve for the variable that's in the exponent. I think I just heard you say logarithm. So what we're going to do is we're going to divide both sides by P. And since the P goes away entirely, and we're left with 1/2 is equal to e to the 5,730r, it actually doesn't matter how much you started out with for this half-life business. Half of what you started with is half of what you started with, no matter how much you started with. Because I have a variable and an exponent, I'm now going to apply the natural log to both sides. And so on the left-hand side, we have the natural log of 1/2. On the right-hand side, we have that cancellation property because the base is e and I have e to some exponent, right? So this becomes natural log of 1/2 is equal to 5,730r, which then means that r is equal to the natural log of 1/2 divided by 5,730. If I needed this value right now, somebody asked me the rate of decay, I'd put that into a calculator, but I'm not going to do that right now. I'm going to leave it as is. I know it'll cause more writing later, but it'll make sure that our answer is more accurate. Now let's go back to our original scenario. We had 2.4 grams that became 1.3 grams through radioactive decay. That rate of decay was what we just found due to the half-life. And so what we can do is we can flesh out the equation and it'll look like this. 1.3, which is what it ends up being, is equal to 2.4, which is what it started out at, times e to the natural log of 1/2 divided by 5730, that's the r that we just found, times t. And t is the variable we want to solve for. So remember, we just did all that to find r so that we didn't have too many variables in the equation. We only wanted one. Well, now I'm going to basically take the same steps I took a minute ago. We're going to get the exponential factor all by itself, and then solve for the variable that's in the exponent. To do that, I'm going to divide both sides by 2.4. And because I'm going to be putting this into my calculator in a minute, I'm going to leave it as 1.3 divided by 2.4. We'll just keep writing it like that. Is equal to e to the natural log of 1/2 divided by 5730 times t. Now, because I have a variable and an exponent, I'm going to apply the natural log to both sides. So natural log of 1.3 divided by 2.4, after using the cancellation property, is equal to the exponent natural log of 1/2 times 5730t. And so applying the natural log to both sides, we get the natural log of 1.3 divided by 2.4 is equal to the natural log of e to the natural log of 1/2 divided by 5730 times t. We have that cancellation property of logarithms. And so this equation now becomes natural log of 1.3 over 2.4 is equal to the natural log of 1/2 divided by 5730 all times t. Well, I have a thing times t and I want to solve for t, and so I'm going to divide by that thing, which to me means I'm going to flip and multiply. So t is going to equal 5,730 times the natural log of 1.3 over 2.4 all divided by the natural log of 1/2. That's going to go into my calculator. And I get that t is approximately 5,068 years. When I put this into my calculator, by the way, in the numerator we had the natural log of 1.3 divided by 2.4. I had to put parentheses around that. In the denominator where I had natural log of 1/2, I actually entered that in my calculator as 0.5 because I didn't want to deal with the parentheses. So that's just, something you can do. In any case, does my answer make any sense? 5,068 years. Well, if we look back at what we were told that the half-life is 5,730 years. If I started with 2.4 grams, then it would become 1.2 grams after 5,730 years. So to become 1.3 grams in an amount of time that's less than the 5,730 years seems to make sense to me. Next, another radioactive decay problem. We have if 80% of a radioactive element remains radioactive after 250 million years, then what percent will remain radioactive after 600 million years? And we're asked for the half-life of the element. So since we're told something about 250 million years and we're asked something about 600 million years, what we're going to do is we're going to say t is in millions of years. As long as we're comparing apples to apples, that's actually an okay thing to do. Now, what's up with them telling me that 80% remains radioactive? Well, if I started out with some amount p, and 80% of it is still radioactive, then that becomes 0.8 p, right? Or 0.80 p, 80% of the sample is still radioactive. And I'm told that that's what happens when t is 250. Remember, it represents millions of years. So using our radioactive decay model, A equals PE to the RT, our A is 80% of P. I'm dropping the 0, so just 0.8 P is equal to PE to the r times the amount of time it took to do that, 250 years, or 250 million years. So this should resemble the previous problem. The steps are darn near identical here. We're going to divide both sides by p, get rid of it, so it doesn't matter how much was in the sample to begin with. We just need to know the ratio, 80%. And so 0.8 is equal to e to the 250r. So the same steps that we took before will give us that r is equal to the natural log of 0.8 divided by 250. Now that's in millions of years, or if we were to give an answer as to what the rate of decay is, we would say, r is whatever percent per million years. But it doesn't matter, because we were asked to find out what percent remains after 600 million years. So we want to find a when t is 600. For that, we're going to write down a is equal to pe to the rt. Well, I kind of fibbed a little bit. We don't really want to find a. We want to find the percent that remains. We actually want to find a over p, which, by the way, is equal to e to the rt, and we just found r. So, the percentage that remains, a over p, is equal to, well, that's the fraction that remains. The percentage will be obtained by multiplying by 100. You'll see that in a minute. But a over p is equal to e to the natural log of 0.8 divided by 250 times, we wanted to know how much would remain after 600 million years, and so there it is. This doesn't even require a log. My calculator tells me that a over p is 0.585. We were asked for a percent, and so I'm going to say 58.5% remains radioactive. And that answers that question. But wait a minute, let's go back. There was another question. What is the half-life of this element? Remember, half-life is the time that it takes for the amount that you had to become half of what it was. So we have this r that we're going to end up using. So what we now have is 1/2 of p, that's how much you have when you have half left, is equal to pe to the r, which is the natural log of 0.8 divided by 250 times t, and we're trying to find out what t is. We're going to use, I feel like a one-trick pony here. We're going to divide both sides by p, and so we have 1/2 is equal to e to the natural log of 0.8 divided by 250 times t, and using the same steps that you've seen, I get that t is equal to 250 times the natural log of 0.5, just ease of calculator stuff, divided by the natural log of 0.8, which my calculator is going to tell me is about 776.57. But remember what t was. T was in millions of years. So we're going to say 776.57 million years. And I'm actually going to phrase this in a full sentence. The half-life is about 776.57 million years. How many decimal places? How accurate do we need to be? Do we have to say about? Tell you what, ask the chemist or the anthropologist that needs this. I don't know. I can say, though, that there's something that I should have caught a few minutes ago, and it's when we did the a over p here, I should have said squiggly equals. In other words, our answer was approximate. The calculator didn't just say 0.585, I rounded. Now we turn our attention to an investment problem. A woman invests $6,500 in an account that pays 6% interest per year, compounded continuously. We want to know the amount after 2 years, and then how long it takes for it to be $8,000. Since it's compounded continuously, we get to use A equals PE to the RT. After 2 years, well, wait a minute. What is the information we've been given? The $6,500 is the P. The interest rate is 6%, and so we're going to say that R is equal to 0.06, right? Remember, we have to express that as a decimal. And then if we want to know the amount after 2 years, then that value is going to go into T. So the amount that we have, if you like, we can do like A of 2, right? The amount after 2 years is equal to the $6,500 that's initially invested times E to the R, which is 0.06, times T, which is 2 years. This goes straight into my calculator, which tells me that the amount after 2 years is about $7,328.73. Since this is money, I should use a dollar sign. There we go. How long will it take for the amount to be $8,000? Probably more than 2 years, right? Because, you know, 7,300. We have the same interest rate. We have the same PERT. We have the same initial investment. This equation now becomes 6,500 times e to the 0.06t on one side, and on the other side we have the $8,000 that we want it to become. I bet you know what we're going to do. We're going to first solve for the exponential factor, and then we're going to use logs to solve for t. So we're first going to divide both sides by 6,500. Now this is going to my calculator, so I don't need to reduce completely, but look, why do I need to type in zeros if I don't need to type in zeros, right? So we have 80 over 65 is equal to e to the 0.06t, and now I'm going to hit both sides with the natural log and then divide by 0.06. And so I have the natural log of 80 over 65 divided by 0.06 is equal to t. And so t is going to be approximately 3.46 years. As expected, longer than 2 years. Next, another investment. Find the time required for an investment of $5,000 to grow to $8,000 at an interest rate of 7.5% per year, compounded quarterly. Compounded quarterly, that means that A is equal to P times the quantity of 1 plus R over N to the NT, where in this case, our P, the amount invested, is $5,000. Our A, the amount we have after time, is $8,000. Our interest rate is 0.075, and compounded quarterly means that N is equal to 4. We're told to find the time, which means we're going to solve for t. So we've got 8,000 is equal to 5,000 times the quantity of 1 plus 0.075 over 4 to the 4t. Same steps as before. Why don't you pause the video, see if you can bring this home. Okay, so maybe not exactly the same steps. First, I divided by 5,000 to isolate the exponential factor. I reduced the zeros, and I have 8/5 is equal to 1.01875 to the 4t by putting the quantity that was in parentheses into my calculator. Now, since I have a variable in the exponent, I want to use a log. I don't really want to use a log base 1.01875. I'd have to use the change of base formula, rather avoid that. So I'm going to find the natural log of both sides. Well, not find it, but apply. And then the exponent, the 4t, I'm going to bring that out front as a coefficient. So we have natural log of 8/5 is equal to 4t times the natural log of 1.01875. At this point, let's remind ourselves that we are solving for t. And so what I want to do is, I want to recognize what's going on. I have 4 times t times the natural log of something. Since that's a bunch of times, what I want to do is I want to divide out everything that's not t. So I'm going to divide both sides by 4 times the natural log of 1.01875. On the right-hand side, the 4 divides out, the natural log factor divides out, and I'm left with t. On the left-hand side, I have something that I'm going to put into my calculator, but I should write down the exact answer. So t is equal to the natural log of 8/5 divided by 4 times the natural log of 1.01875. Now, as a calculator answer, I'm going to get the t is approximately 6.33 years. Now, that's good enough for me. Okay, fine. If we wanted to be fancy, we could take the 0.33 and multiply it by 12 to find out how many months it'll be. And since 0.33 times 12 is about 4 months, we can say that the 6.33 is about 6 years and 4 months. That's just if you want to show off. Next, we have a problem that's going to require something called Newton's law of cooling. We have a thermometer reading 72 degrees that's placed in a refrigerator where the temperature is a constant 38 degrees. We're asked if the thermometer reads 60 degrees Fahrenheit after 2 minutes, what will it read after 7 minutes? Well, as I said, this is going to require Newton's law of cooling. And some books give a slightly different model, but it means the same thing. Here I've got Newton's law of cooling as T of t is equal to T sub s plus D sub 0 e to the kt. What the heck is going on? First off, the uppercase T is temperature. The lowercase t is time. Okay, and the lowercase t is the input variable. K is a constant. It's related to the air temperature, the substance that's cooling, and all of that. It's dependent on the situation. It's something that we would have to find every time we work something out, and we're going to do that. E is, of course, Euler's number, the familiar number. D sub 0 is the initial difference between the thing that's cooling and the outside temperature. So if we're talking about a dead body, the body was usually at, say, 98.6 degrees, and then you have an outside temperature. You would take the difference there, and that would be D sub 0. In this case, we have a thermometer that was at 72 degrees, and it's going to 38 degrees. And so what that tells me is that D sub 0, the initial temperature difference, is 34 degrees. And then there's this T sub s. T sub s is the surrounding temperature. And so the refrigerator's temperature, in this case, T sub s, is equal to 38 degrees. In the case of the dead body, that would be the surrounding air temperature, assuming that it stayed the same for the whole time the body was dead. Now we know what all these mean. Let's look at our model. Our model in this case is going to be T of t is equal to the surrounding temperature of 38 degrees plus the initial temperature difference of 34 times E to the K, which we're going to find, and then T is going to be an input variable. Here we're told at first that the thermometer reads 60 degrees Fahrenheit after 2 minutes. That 60 degrees Fahrenheit is the temperature after some time, and that 2 minutes is the T. So we get an equation that looks like 60 is equal to 38 plus 34e to the 2k. That's just putting in the information that I have. Based on this, since there's only one unknown here, k, I'm just going to go ahead and solve for k by first isolating the term that has the exponential factor, and then isolating the exponential factor itself, and then finally solving for k. What that means to us is, first we're going to subtract 38 from both sides, and get that 22 is equal to 34e to the 2k. And then we're going to divide both sides by 34. I'm going to go ahead and reduce that, because there's not really any reason not to. 11 over 17 is equal to e to the 2k. And now I'm going to Apply the natural log to both sides. And we're going to get that K is equal to the natural log of 11 over 17, all divided by 2. That's the constant for this situation, the rate of temperature change, if you will. Now we're asked, what will it read after 7 minutes? And so we need to put all this back together and find T of 7. The surrounding temperature of 38 degrees hasn't changed. The initial temperature difference of 34 degrees hasn't changed. Well, that hasn't changed for since it started. K is what we just found. The natural log of 11 over 17 divided by 2. And then in place of T, we have 7. This goes straight into the calculator. And so what we get is the temperature after 7 minutes, and there I go hitting equals again, I mean approximately 45.4 degrees Fahrenheit. Does that make sense? Well, let's see. If we chart temperature over time, we started out at 72 degrees. After 2 minutes, we were at 60 degrees. And then after 7 minutes, we were at 45.4 degrees. It's cooler, so it seems to work. It should also make sense that as it gets cooler and cooler, it's trying less hard to get cooler, right? The temperature difference isn't the same, and so it doesn't need to cool off as quickly as time passes. So let's go ahead and circle that answer. And now we're asked, how long will it take before the thermometer reads 39 degrees Fahrenheit? So that means that we're looking for T of T to equal 39 degrees Fahrenheit. That's the output if all of the other stuff is the same. That is to say, the surrounding temperature is 38 degrees, the initial temperature difference was 34 degrees, and then we have E to the natural log of 11 over 17, all divided by 2, times T. Since we're asked how long will it take, it should make sense that we're solving for T. Well, let me erase that T of T so it doesn't look confusing. And now we're back in a very familiar place. We're going to solve for that T in the exponent. Why don't you see if you can pause the video and do this yourself? Okay, so I subtracted 38 from both sides. That left me with 1 on the left-hand side. Then I divided both sides by 34, and so I have 1 over 34 is equal to E to the natural log of 11 over 17 divided by 2 times T. Now we're going to apply the natural log to both sides using that cancellation property of logarithms. And here I end up with, let me erase that arrow so it won't confuse me. The natural log of 1 over 34 is equal to the natural log of 11 over 17 divided by 2 times T. When I flip and multiply, I get T is equal to 2 times the natural log of 1 over 34, and that's divided by the natural log of 11 over 17. When I put this in my calculator, I get that the time is about 16 minutes. Now, does that still make sense? Well, let's see, let me circle that and then go up here to the graph that we had. When it started out, it was 72 degrees, and then after some time, it was 60 degrees. After some more time, it was like 45 degrees. And then after 16 minutes, we're down to 39 degrees. This is making total sense to me. It's decreasing over time, and the rate at which it's decreasing is decreasing. Whoa. And at this point, I'm going to plead your indulgence because this little drawing that I made is not to scale. What happens to the temperature as time passes? Well, eventually, it's going to reach the 38 degrees. See, what we have here is a horizontal asymptote at the value of the temperature is equal to 38 degrees Fahrenheit. That's the temperature of the refrigerator. We had an initial temperature difference and a temperature change that's slowing down over time. It won't be the case that the thermometer will all of a sudden dip below zero. You see, it just doesn't make sense. It's going to try to become the temperature that the refrigerator is. When I say try to become, I mean, look, after a week, the thermometer is going to match the temperature of the refrigerator. So that's where a mathematical model runs out of its usefulness. It eventually, the temperature will actually touch, right? So that's just reality. But the mathematical model has a horizontal asymptote, which should make sense. The temperature, T of t, was equal to 38 degrees plus the 34 times e to the kt. Yeah, we found out what k was, but that's not what I'm after here. What I see here is an exponential function that has been raised up by 38 units. And so the horizontal asymptote should make sense. Anyway, as time passes, the temperature will approach 38 degrees Fahrenheit. And that's good enough for me.